Hi everyone, thank you for tuning in to watch our video about recycling batteries. We are students of the Chemical Engineering Program class of 2021 from the University of Cincinnati. Today we will talk about the recovery of valuable metals such as zinc and manganese from spent alkaline and zinc carbon batteries. These are the batteries that are usually used in everyday uses in most consumers' household and other products such as toys, electronic products, electronic devices, or other. My name is Mohamed Al Masri. My team is Wesley Black, Terrell Stewart, Ben Schroeder, and Efe Alou. I will take 10 minutes to briefly describe our project. So the main project objective is to mainly recycle the batteries, but we know batteries um, have toxic metals inside them, and when they are not recycled, they are likely to end up in landfills where they will contaminate, they will leak and contaminate any natural resources like groundwater, soil, anything close by. Um, the battery recycling process here is goal is to actually recover zinc and manganese from the alkaline and carbon and zinc carbon batteries to get zinc sulfate and manganese sulfate. These are two solid chemicals that are in large demand in most chemical specialty industries, fertilizer industries, and including pharmaceutical products. In fact, the product that we make in this project are pharmaceutical grade, which means they are more than 99.99% pure. This is an overview of the project. So we collect the batteries from recycling sites or waste management sites. These batteries then go through mechanical crushing or a mechanical process. They will be sorted out, they will be crushed, ground, and sieved so to obtain the black powder inside them. This black powder contains a large amount of graphite, zinc oxide, manganese oxide. For other batteries, they may contain um, lithium oxides and other metal oxides. All these elements are likely metals, metal oxides, and in this process, we will react them with sulfuric acid and sulfur dioxide. This process is called acid leaching and it belongs to the hydrometallurgy or hydrometallurgical chemical route. Compared to the other chemical route, there's a pyrometallurgy, which consumes a lot of energy to basically heat all the metals and melt down everything and separate them. These are the final products in this project: zinc sulfate or zinc sulfate heptahydrate and manganese sulfate or manganese sulfate monohydrate. These are largely in demand in most of these industries and other industries. The proposed project consists of main processes within: washing, reacting, filtration, and crystallization for each product. First, the black powder is washed with water to get out any soluble compounds like potassium hydroxide. The first reaction, we add sulfuric acid, which is concentrated, to obtain zinc sulfate solution with the other solids. This stream then goes through filtration to get the zinc sulfate solution, which is then crystallized and we obtain the final product. The other solids, which still have the manganese dioxide, go through the second reaction and we add sulfur dioxide to obtain manganese sulfate solution with the other solids. This stream then goes through filtration and purification where we get out the solid waste and we get out the manganese sulfate solution. The manganese sulfate solution is then crystallized to obtain the final product. This is just a short summary of the process flow diagram. This is a detailed process flow diagram which shows the final design of the proposed process. I will explain this briefly. First, we start with adding the black powder into a solid wash with large amount of water to get out any impurities and as filtrate. This step is necessary to get out the impurities as they may adversely affect the crystallization processes we have later. This then goes through the first reaction step where we add concentrated sulfuric acid. We then get out zinc sulfate solution as well as other suspended solids. We then go through another step of washing and filtration where we get out the solids and we separate zinc sulfate. The zinc sulfate solution separated then goes through crystallization process, which is cooling crystallization. After forming the crystals, this goes through an extra filtration and washing step, and then it ends up with drying to get out all the moisture and end up with our final product of zinc sulfate heptahydrate, which is 99.99% pure. Suspended solid from this filtration step which still have the manganese dioxide that we need for the second step, go through the second reactor where we add sulfur dioxide. Sulfur dioxide react with manganese dioxide to form manganese sulfate. Manganese sulfate solution with other solids is washed and we obtain the solid waste, which is properly disposed of. The solution then goes through an extra filtration step to purify the manganese sulfate and then goes through evaporative crystallization process where we form the crystals. Crystals then go through an extra filtration step and washing step. The last step here is drying, and then we end up with our final product, which is manganese sulfate monohydrate, which is also 99.99% pure. These two flash drum vessels are used to separate unreacted raw materials so we can recycle them back into the reactors and separate water to make sure that sewer water is actually clean and can be disposed of.
Hi, I'm Terrell Stewart, and I'm a chemical engineer student, and I'm the co-PHA lead. I'll start off the process safety with methodology. The methodology chosen for this process hazard analysis was a what-if checklist. With this what-if checklist, we used nodes and created what-if scenarios to identify process hazards and safety measures within the process. Now this would create a safe and simple process, and with this we have created standard operation procedures, safety protocols, and preventative hazard guidelines. All of this will help keep our operators safe.
For process safety, we also had to take into consideration safety devices. Such devices consisted of PID controllers, temperature controllers, flow controllers, as well as relief devices for pressure, control valves, and interlock systems, and increasing pipe thickness. And the increased pipe thickness helped as a solution for corrosive acids or to stop any material from leaking. For temperature controls and flow controllers, this allowed us to monitor the rate at which the flow was going through the pipes and through the system, and monitor the temperature values. That way we didn't get any extreme temperatures with an emergency stop system in case there were overflooding or overflow of liquids, or if the temperature range got out of control, we had safety measures into precaution.
This is a quick overview of some information about the emissions of the project. The project will emit some greenhouse gas, like mainly carbon dioxide from burning fuel, but it is indirect because we will only be using electricity. So depending on the source of the electric, we will be buying some power provider they use coal, some power provider use more renewable processes as they are being implemented here on in the next 10 years. So it really depends. We are implementing a life cycle analysis study to make sure that responsible choices are being made in that sector. But about other emissions, such as acids and whatnot, there's a very low amount of emissions here, and we will go to the next slide.
I'm Wesley. I performed the economic analysis for this project. The total revenue was found to be $16.9 million, and the after-tax profit was found to be $7.7 million. Both sulfate products were assumed to be a pharmaceutical grade. Their prices for their anhydrous weights are listed on left. The main utility cost came from an hourly usage of 709 kilowatts, which cost $304,000 annually. The demand for heaters in terms of electricity was based upon a 1-to-1 joule heating, and the electric demand for motors was based upon the motors operating at 3,600 RPM and a torque estimated as their hourly flow rate at a distance of 1.5 feet. The black battery powder was assumed to have no net cost, as any transport costs could be offset by waste credit, and that the client pays us to take the waste off of their hands. The total capital investment was found to be $10.2 million, with a working capital of just about $2 million. The return on investment is an impressive 94% thanks to the minimal material costs. The venture profit is $5.9 million, and the internal rate of return is 52.4%. For expenditures, it was assumed there were 8,000 operating hours per year. There are 6 operators needed per shift for all equipment, and 5 shifts total. There are 10,000 pay hours with overlapping shifts. On site, there is enough storage to hold 16 hours of liquid feedstock. Most equipment is made out of stainless steel alloy 316 to withstand the acidic conditions, and spare parts are strongly recommended for strongly acidic or coarse particulate environments which will wear down the equipment quickly. The payback period was found to be a rather brief 4 years.